Can you hear me? Hey. Hi. So I would like to thank the organizer for this opportunity. I would like to tell you about some work I've done in collaboration with Gerd Wali, Juan Sebastian Bermudez, Florian Kunel, and Oleg Kaikov. And the idea is that perhaps vorticity could be an interesting substructure of black holes. Okay? How do I go on? Okay, there are two independent lines of argument of how this comes out to be. The first line of argument relies on the N portrait, which is the idea that black holes are condensates of marginally bounded gravitons. And this offers some microscopic understanding and interpretation of some of their key essential properties, okay? And I'm not going through them now, but the natural question is that we know that Bose-Einstein condensate in laboratory, when they rotate, they display vorticity. So it's natural to ask in this picture whether the same can happen when black holes rotate, if they are Bose-Einstein condensates of marginally bounded gravitons, okay? The second line of argument has to do with, is completely independent, and it's related to the fact that there is a class of objects in a renormalizable field theory that display the key essential properties of black holes. And what I mean by that, this class of objects are found out to be the following. Namely, there is an upper bound on the area a localized configuration can attain, and this bound on the entropy is given by its area, okay? When this entropy bound is saturated, so the object obtains an entropy area law, we call this object as Saturon, and what we discover is that whenever we build these objects and we saturate the entropy area law, we obtain the key essential properties of a black hole. Namely, we obtain an Hawking emission, we obtain a notion of page time, we obtain a notion of horizon, okay? And, okay, these objects can be built in renormalizable field theory. And for example, the prototype model I will focus on is a global SUN symmetric bubble. This is where we do calculations, okay? And the idea is that, okay, this provides a useful theoretical laboratory to microscopically understand the properties of a black hole. And as a bonus, we can use them to perhaps predict new features, okay? So what it turns out is that when these objects rotate, they form vorticity. And so we use these objects to understand. So I would like to give you an example of how these can be laboratories and how we can predict new features such as vorticity. So the main point is that we found out the following. When we have a saturated bubble that displays an entropy area law that rotates, it has a maximal spin. And this maximal spin turns out to be equal to its entropy. This turns out to be equal to the extremality bound that we know for black hole. In black hole, this extremality bound emerges from a requirement that we don't have naked singularity. In this microscopic theory, the bound emerges as a requirement of emergence of vorticity. So we have a topological understanding of how this bound comes out to be at a microscopic level. Moreover, whenever we look in these saturated bubble objects, what happens to the soft emission due to the scattering constituents, this stops being present when vorticity forms. So we have also a topological understanding of why Hawking radiation is absent, okay? So up to now, I've told you only about specific property, about facts, that there is a class of objects that has the known properties of a black hole, okay? Now it's about interpretation, namely, can this vortex structure that we observe here emerge also in black hole? This is a conjecture, and the question is, okay, we conjecture it, of course black holes are very special, but can there be phenomenological consequences, okay? So we looked at the merger of these objects, which is interesting from a generic point of view of bubble merger, so we just scatter them, and in some cases, depending on the parameter space and kinematical parameter space of the theory, we can localize vorticity, okay? And so we can look at the energetics of this merger, and okay, the main point is that the energetics vary macroscopically due to the fact that the vortex is a macroscopic feature at the substructural level. And this is reflected in the gravitational wave of these objects, which I'm characterizing on my poster, and it's actually ongoing work, and we hope to be able soon to give exact features for for black hole merger in the gravitational counterpart. So yeah, this is my endpoint. I hope, yeah, thank you.
Time for very short question or comment? I do not see any, so let us thank the speaker again.